Hi everyone, my name is Vlad and today we will learn how to find a Fibonacci number using recursion and iteration. Let's start. What is a Fibonacci number? Every Fibonacci number is the sum of two previous Fibonacci numbers. By convention, 0's Fibonacci number equals 0. First Fibonacci number equals 1. And we can take it from here. So, for example, second Fibonacci number equals 1 plus 0, 1. Third Fibonacci number equals 1 plus 1, 2. And so on. You start to notice a pattern, right? We can generalize this to the following formula. Fibonacci number at position n equals Fibonacci number at position n minus 1 plus Fibonacci number at position n minus 2. And we will use this formula for our recursive algorithm. For our recursion, we already have a general case over here. What about the base case? We know that Fibonacci number at position 0 equals 0 and first Fibonacci number equals 1. Let's take a look at an example. Say we need to find Fibonacci number of 4. According to this formula, this will be equal Fibonacci number of 4 minus 1, 3, plus Fibonacci number of 4 minus 2, 2. Now Fibonacci number of 3 equals Fibonacci number of 2 plus Fibonacci number of 3 minus 2, 1. Fibonacci number of 2 equals Fibonacci number of 1 plus Fibonacci number of 0. And the same thing over here. Fibonacci number of 1 plus Fibonacci number of 0. Here you can see that we have reached our base cases. So we can wrap this recursion back. Fibonacci of 1 returns 1. Fibonacci of 0 returns 0. So this function, Fibonacci of 2, will return 1 plus 0, 1. And Fibonacci of 1 returns 1. So Fibonacci of 3 will return 1 plus 1, 2. And the same thing over here. Now we can find Fibonacci of 4, which will return 2 plus 1, 3. And that's our answer. What about time and space complexity of this algorithm? Let's take a look at the computation of Fibonacci of 5, for example. As you can see, our function calls two other functions at each stage of the computation until we reach our base cases over here. And if you look at this structure, you will realize that this is actually a binary tree. Let's see how many levels are in this tree. It's 1, 2, 3, 4, 5. So this tree has 5 levels. At some points it is incomplete, but for our big O analysis it is fine. So we know this is a binary tree. It grows exponentially and it has number of levels proportional to our integer n. So our time complexity is exponentially as well. It is big O of 2 to the power of n. What about the space complexity? In order to understand the space complexity of our program, let's visualize what's happening with the memory stack during this computation. So we're finding Fibonacci of 5. So first, this function is called Fibonacci of 5, and it gets placed on the memory stack over here. Then function Fibonacci of 4 is called, and it gets placed on the memory stack. Fibonacci of 4. Then, in the similar manner, Fibonacci of 3 is called and placed on the memory stack. Then Fibonacci of 2 is called. And then function Fibonacci of 1 is called. Fibonacci of 1 is our base case, so no more functions will be called after that. And as you can see over here, none of these functions have returned any values yet. So this is the size, the height of our memory stack at the top point in the computation. And as you can see, the size, the height of this stack is proportional to our integer, 5 in this case. Now let's just try to see what happens next. So function f of 1 will return some value, and it gets taken off the memory stack. Then function f of 0 will be called, and it gets placed on the memory stack. And then function f of 0 will return the value 0, and it will be taken off the memory stack. Now we know the value of function f of 1, and we know the value of function f of 0, so function f of 2 will return the value, and it will be taken off the memory stack. And our computation goes on in the same manner. So the space complexity of this algorithm depends on the size of the memory stack, and the size of the memory stack is proportional to our integer n. So we can say that space complexity is linear, big O of n. In the next video, we will take a look at slightly more complex but optimized version of this algorithm. For the iterative algorithm, we know 0's Fibonacci number, which is 0. First Fibonacci number is 1, so we can simply find the next Fibonacci number, which will be 0 plus 1, 1. And then we can find the next Fibonacci number. So third Fibonacci number will be 1 plus 1, 2, and so on, until we find the nth Fibonacci number. So in other words, to find the nth Fibonacci number, we can build up our computation on the Fibonacci numbers we already know. Let's analyze time and space complexity of this algorithm. We're making n steps in order to find nth Fibonacci number. So our time complexity is linear, big O of n. The space, actually it depends on the implementation of the algorithm, but in our case we will keep this whole sequence of previous Fibonacci numbers in memory, so our space complexity will also depend on n, and it will be linear as well, big O of n. In the next video, we will improve on the space complexity, so stay tuned. But for now, let's write some code. Our recursive implementation is relatively straightforward. Let's define a function fib that will take integer n as an argument, and let's put our base cases first. So if n equals 0, we will just return 0, and if n equals 1, we will return 1. And for the general case, we will just return the sum of two previous results. So fib of n minus 1 plus fib of n minus 2. Now let's quickly test this function. Let's find all Fibonacci numbers from 0 till 8. So for n in range 9, let's print the position and the number itself. And let's run this code. And as you can see over here, the results are as expected. The one thing to keep in mind that this particular recursive algorithm, without any optimizations, has exponential time complexity. So if you try to find, say, Fibonacci number of 35, you will see that this function took a little longer to compute. And if you try something like 50, you will wait for a while to finish the computation. So that's something to keep in mind. For our iterative implementation, let's define the function fib that will take integer n as an argument. And as you remember, in order to find nth Fibonacci number, we need to know the whole sequence of previous Fibonacci numbers. So let's create a list and fill it with zeros. And the only question is, what should be the length of our list? For example, you need to find third Fibonacci number. For that, you will need to know 0th Fibonacci number, first Fibonacci number, second Fibonacci number, and then you will also store the third Fibonacci number in the list. So in total, you will store 4 Fibonacci numbers in the list. So the length of our list will be n plus 1. Now let's write down our 0th Fibonacci number, which is 0, and first Fibonacci number, which is 1. And we will iterate over the rest of the list, starting from the second element, and go upwards our number n. And we know that Fibonacci number at position I is equal to the sum of two previous numbers. So result from I minus 1 plus result of I minus 2. And in the end, we will just return Fibonacci number at position n. The only thing to keep in mind in this code, if you try to find Fibonacci number of 0, the length of your list will be just 1, and this line will cause an error. That's why we'll add a quick if check here. So if n equals 0, we will just return 0. Now let's quickly run this code. Let's find all Fibonacci numbers from 0 till 8. And we will print the position and the number itself. Let's run this code. And as you can see, the results are correct. And this code doesn't have exponential time complexity, it has linear time complexity. So if you try to find Fibonacci number of, say, 1000 or even 10,000, you will be able to do that. Let's give it a quick run. And as you see, yeah, the results are very big, but yeah, that's the Fibonacci number, the 10,000th Fibonacci number. Thank you for watching this video. If you found it helpful, press that like button. If you have any ideas or suggestions, please post them in the comment section down below. Thank you, and I'll see you in the next one.